Welcome again in the Global Lecture Hall for the third lecture of our 2014 edition. Today we have another interesting session with two guest lectures and a student's presentation and the presentation of a site, by the way, of a Russian University for the Humanities. Actually, we didn't, like we did in past years, have a long hour, half and a half dedicated to the presentation of a site. But if you wish, we can allocate a few minutes in each lecture for the presentation of other sites. So the topic of today, today we will have three, as you have seen from the program, we will have three main lecture. One in the basic thread following the lecture from by Rolf in the past weeks, and the topic will be the design. So we will start to discuss which kind of design principle we should follow to design an artificial intelligence in the wise way that we are pushing, no? That Rolf basically has been pushing and is pushing for many years. So how we really can take care of embodiment into the design of intelligent systems. And because I think that Rolf have shown clearly enough already how it is not easy at all how to give a definition of intelligence. So it may be too much to say that we have, after 50 or 60 years by now of attempts, we have not still achieved artificial intelligence, because we may have been following in many cases let's say a not completely appropriate paradigm. But let's take this point of view. So since it's so difficult to define intelligence, it can be of great help to use the so-called synthetic methodology. Now, the synthetic methodology means with respect to the psychology or biology or neuroscience approach, is an approach when based on some principles, and we will start to discuss this principle that we can use and some use, and probably in the future we will have to use more in the design of intelligent systems. We can build an artifact, a system, an artificial system, which actually shows the behaviors of a natural system. This is when you a very valuable approach when you have to study system of a complexity. I don't mean of a human brain, but of a simple animal like a spider or an ant. Because we usually say that ants are stupid, but ants have a complexity of behavior which is so far unmatched by an artificial system. So, and this method is actually an engineering method, and it's the method of artificial intelligence and cognitive science. So the idea of a synthetic methodology is that you really understand something when you build it. But even given that, we know that there have been some artifacts built in the past which simulated the behavior of a human. So humanoid robotics is very old. If you look to this old Swiss automata of the end of the 18th century, or you look to the Japanese karakuri dolls, you see that a mechanical simulation of human behavior has been already attempted. Is this idea of putting, and the computer in a Karakuri doll was actually a complex system of gears and leverage and belts connected in a smart way, and the results were actually amazing. But is this enough? So if so, let's now let's have a look at a couple of video. The first one is quite famous, I think, on YouTube, and is what I called an excellent robot that day. So, Nathan, maybe you can show the first. Briefly show. Right now, this is an old video because it's 7 years old, more or less. And I'm sure you have seen very, and you can find, if you look for Honda Asimov in YouTube, we will find many amazing new movement possibilities of this machine. But what we see here is probably still a problem. If you remember, or you want to have a second look you want to watch again the presentation that Rolf gave last time, the problem with building a robot like this, so a computer system, okay, thanks. No, so the problem here is that this robot falls in a very unnatural way. So, of course, we can now, Nathan, can you show the next one? So, of course, you can complicate the machine. So you can add many security loops, many control loops in addition to those that were there, and this has been done. But you easily impact with the frame of reference problem that was apparent in the discussion of Dennett's automaton trying to stop a bomb, right? So of course you can add more and more routine, considering more and more cases. But what you really miss in this kind of approach is the possibility to deal with unexpected, with open-ended environment. And what really happens is that we are always acting in an environment which is open-ended. This means that it continuously rise new issues and challenges which are not that you cannot think in advance when you design the system. So why this other video is interesting? Because this is a very small part of the inner life of the cell. So this simulation is based on real scientific data. No? It's a visualization of things that we strongly believe, I mean, biologists studying these things strongly believe are happening in the cell. What you really see at first glance is that the model of working, the paradigm of design is improper. No? The paradigm of the life form evolved naturally is completely different. So it's clearly based, it's highly stochastic, it's based on many parallel processes. It systematically uses soft robots. So the problem that we are not going to solve, give you the solution this lecture series, but will take probably the research of a generation, is how we will be able to design robots, artificial intelligence, based on this new principle. And so this is something that is an open issue, and that's why we really value interaction from the participants, because on one side we try to touch some basic points. On the other side, we wanted to show you the basics, so some really frontier research work, which is typically presented in the guest lecture. So this is okay for this. So a big issue, for instance, is, and we may have a student's presentation or an open discussion of this, is so to have cognition, I first need life. We don't know, right? So you remember, to introduce the student presentation from Xiang, you remember that actually in the past lecture, Rolf raised some doubt about how we can measure intelligence. No, is the IQ okay? So it's enough to do the IQ to a robot, so we know that it is intelligent. And this might be a first idea, and it immediately. And I would like to have some student presentation on this too. Of course, we see immediately that there are people with very high IQ which have a clear professional success, even in sciences. On the other hand, we see examples of people who have not so high IQ, who are very successful professionally and even in science. No? Or, I mean, you know that Einstein used to say everybody that his IQ was 130. So 130, for your, if you don't know, is more or less the average of engineering students or science students when they finish their study. Why? Because we have to learn to cope with many formal problems when you study certain kind of disciplines. No, so it seems to have a bias there. So not surprising, at the very beginning of AI, Turing came up with the Turing Test, which is a kind of operational way to see if a system is intelligent. So I talk to the system without seeing it. If it can fool me and convince me that it's humans, well, so this is a very simplified version of the Turing Test. But the idea is that I put the system behind a wall, and then I interact with the system. If he is able to fool me, question, how many times? Who? Me and Francesco, me, Nathan and Francesco, everybody, 3 years old. So it's something which needs to be refined, no? But this is the idea. So I don't know how intelligence works, and so I come out with an empirical criteria to define intelligence. And then there was this, and here I'm introducing the student presentation. There is this thing that, of course, in a Western context, Charles Searle raised an objection to Turing, say yes, but let's think that I have a kind of automaton inside so put a person like Searle or me, to a very large extent, who doesn't understand any Chinese, and raise questions in Chinese to these people close into the box. He will give answers. If he has a kind of long list, a lookup table where he can match the question with the answer. Of course, this is very Western oriented, no? Because Chinese is a language which in the past was not very spoken in the West. Now I think the situation is just to give you another example before I hope giving the floor to people in Xi'an. No, we may think if the Turing test was proposed in a Chinese-speaking community, probably they would have proposed an English room for the experiment, right? So that's why very nice to see. You know, and just to give a last example of this, in Austria, they used to say, when they really don't understand what you say, they used to say, this is Spanish for me. Well, I'm Italian, so I don't live very far from Austria. I wasn't grow up very far from Austria. But for me, Spanish is an example of a very easy to speak language. Well, maybe my Spanish friends don't agree with me, but about my Spanish, but so this gives you an idea of a relativity also of this kind of experiment. But now I leave the floor to Xiang, where we will talk from China about the Chinese room experiment. So Dustin.
Hello, Nathan. Can you hear me? Okay. Good afternoon, good morning, good evening, everyone. Today, our site will give a presentation about Chinese room problem. We are from Northwestern Polytechnical University at Xi'an, Shanxi Province, China. Xi'an is one of the origins of world civilization. There are many important sites and relics in this city. Yeah. This is our university, NPU. It was founded in 1938. NPU is a research-oriented, multidisciplinary international university of science and technology, and has strong capabilities and outstanding achievements in aeronautics, astronautics, and marine technology, which makes it very unique and distributed from other institutions. Our new campus, the Chang'an campus and UE campus. This is some pictures about my lab, multi-agent robot system lab. The main topics in our lab is about multi-agent robot system, machine learning, computation intelligence, autonomous developmental robotics, real-time artificial intelligence, embodied intelligence. Yes, Rolf visited our lab in 2011. Yeah. Some slides. This is the 5th time we participate in Shanghai lectures. Thanks all. So next, our students will give a short presentation about Chinese room. Okay. Okay.
Okay. Hello, everyone. My name is Chiro Peng, and I come from Northwestern Polytechnical University, and my major is computer science and engineering. And this is my partner.
My name is Wang Cimeng. I also come from NWPU, and my major is also the computer science and technology.
Okay, and today our topic is about Chinese room experiment, which is a famous argument that was raised by Searle. And our presentation today was include 4 parts. In the first 2 parts, I will introduce who is John Roger Searle, and I will introduce some important concepts about this experiment, such as strong AI, weak AI. And after we set up such concepts, we will let Clark to introduce the detailed explanation about Chinese experiment, and lastly we will draw our conclusion. So now let's begin. Well, who is John Roger Searle? He is an American philosopher and currently the professor of philosophy at the University of California, Berkeley. He is widely noted for his contribution to the philosophy of language, philosophy of man, and social philosophy. He began to teach in Berkeley in 1959, and among his notable concepts is the Chinese room argument against a strong artificial intelligence. And we can see Searle is not an engineer or a scientist. He is a philosopher. And in this way, we can see that artificial intelligence is not only an engineering subject, but it also crosses past so many other branches. As a consequence of biological neutralism, is that if we want to create a conscious being, we will have to duplicate whatever physical process the brain goes through to cause consciousness. Searle thereby means to contradict what he called strong AI, defined by the assumption that as soon as a certain kind of software is running on a computer, a conscious being is thereby created. So, what is strong AI? And now I want to introduce this concept to you.
No, go ahead.
Okay, and the term strong AI was adopted from the name of a position in the philosophy of artificial intelligence, first identified by John Searle as part of his Chinese room argument in 1980. He wanted to distinguish between two different hypotheses about artificial intelligence. One is an artificial intelligence system can think and have a mind. Let's focus on this important word, mind. The word mind has a specific meaning for philosopher, as used in the mind-body problem or philosophy of man. And another is an artificial intelligence system can only act like it thinks and has a mind. That means he only worked under the program that we designed for them before. He can't think for himself. And the first one, we call it strong AI hypothesis. And the second, we call it the weak AI hypothesis, because the first one makes the stronger statement. It assumes something special has happened to the machine that goes beyond all of its ability that we can test. And Searle also referred to the strong AI hypothesis as strong AI. And this usage is common in academic AI research and textbooks. And the term AI is now used to describe any artificial intelligence system that acts like it has a mind, regardless of whatever a philosopher would be able to determine if it actually have a mind or not. Now, let's have examples for strong AI. Okay. In this picture, we can see a robot that he can locate his target, and it can also recorrect himself and correct his direction. So he achieved the locomotion and orientation. In some degrees, we can call it strong AI. And we also have a good example for narrow AI. That's Siri. If you have an iPhone, you can use Siri to arrange your schedules to help you to solve some problems. Sometimes we think it's intelligent, but actually it's just a narrow AI. Searle just operates within a limited predefined range, and there is no genuine intelligence, no self-awareness, no life despite being sophisticated. So it's just a weak AI. A famous magazine, Forbes, a famous writer wrote that the iPhone Siri just represents the arrival of hybrid AI, combining several narrow AI techniques plus access to massive data in the cloud. Okay. So we just introduced some important concepts about strong AI, weak AI. And now let's give our time to Clark. He will give you a detailed explanation about that, what the Chinese room experience really is.
Now let's start part 2. In this part, I'll introduce what the Chinese room problem really is and what it tells us. First, simply imagine that someone who understands no Chinese is locked in a room with a lot of Chinese symbols. Then, a program is there for answering questions in Chinese, and the program is so good that the answers to the questions are indistinguishable from those of a native Chinese speaker. The man outside the room gave an input to the system consists in Chinese symbols in the form of questions.
No video either.
It seems they are stuck. The video conference seems stuck. Yes, we can continue your presentation from Moscow. Have you any message? Were you able to send a message by chat to that thing? I see. Okay, so as we note every time, every year, many times video conference is an old technology, but still we have this kind of problems. Maybe we have many sites, but so I think that while we try to get again in contact with Xiang, we can listen to the presentation from Moscow if they are ready in Moscow, which is the site's presentation. They promised to make a student presentation next week. So
we'll make the student's presentation next time.
Are you ready, Moscow?
Yes, can you hear us? Hello? Hello, can you hear me?
Yes,
hello?
Yes, we hear you. Yes.
Yes. Unfortunately, the students couldn't prepare a presentation for today. There will be next time, and we arranged it with you, Fabio, that it was a short notice and our students just couldn't prepare it very quickly. But we'll just have a presentation of our university, a very brief presentation of what we are having at this university in terms of artificial intelligence. And I would welcome the idea of a Russian room. So why not? Not many people know Russian nowadays in the world, so we could suggest it for the future.
Unfortunately, you are right.
Right. So we're beginning our presentation. About the Russian State University for the Humanities. Just hold on a minute, but I can start saying that though we are the leading university in the humanities, we are very proud to have a special department of artificial intelligence and the whole faculty of information technologies, which is not typical of normal Russian university. While they're trying to find to switch on the presentation, I would like to say that it's a real challenge for us, but it's also a great pleasure and a privilege to be involved in Shanghai lectures. Yes, that's it. Thank you. It's the fifth time. It's the fifth time that we are involved. So our university was founded in 1991 on the basis of Moscow State Institute for History and Archives that dates back to 1930. The university comprises 13 institutions, 16 faculties, 95 departments, research institutes, 26 research and study centers, and 14 international research and study centers. About 12,600 students study at our university at the moment. On the picture you can also see one of the know-hows of our university. We have 9 museums. It's education through art, including digital art. Hello? No slide. Okay, I'm very sorry. I thought that you can see the slides. Very sorry. Can you see now? Okay, right. Yes, this is a picture of one of the museums of our university, which is a key feature in the know-how. We have 9 museums on the territory of our university, and art, education through art, is one of the mottos, including digital computer art. And we are involved in several international projects with the European Union, with the European Commission. The latest project, campus project, is in digital art. But now, next please. You know, we are the leading university in the humanities, and we offer training at BA and MA levels in 64 fields, including history, philology, philosophy, psychology, linguistics, anthropology, Eastern culture, sociology, and intelligent systems. And we award doctoral degrees in 52 disciplines. So we started our Shanghai lecture participation in 2010. So it's the 5th time that we started, that we are beginning this lecture. In this year, the students from artificial intelligence, psychology, linguistics, and philosophy have applied for the program, but most of them are from artificial intelligence. Our main research interests: we have a Center for Cognitive Programs and Technologies, and within this center we are working in the fields of cognitive linguistics, cognitive psychology, cognitive philosophy, and artificial intelligence. Next one. Artificial intelligence at our university is concentrating on the following areas. First, machine learning. A famous GSM method of data analysis was introduced by Professor Victor Finn, and this method is applied in evidence-based medicine, cognitive sociology, cognitive forensic science, attribution of historical documents, and pharmaceutics. We are also doing research in computational linguistics, in anthologies, and robotics. And as regards robotics, we have a special center, robotics center, which opened in 2012. The director, Vladimir Pavlovsky, is the key person in Russia in the field. And Tatiana Volkova is a teacher who is also our course leader or teaching assistant in Shanghai lectures. So the main objectives of the Robotics Center is implementing artificial intelligence methods in robotics. A new subject, Introduction to Robotics, has been delivered here since 2010. Next year we are planning to introduce or to start a master program in artificial intelligence robotics. And we are proud of our Robots Park. Maybe it's too much to say Robots Park, but there are a few examples. 6 pop-up bots, you can see it on the screen, then 1 Wowbean robot, and 1 Now robot. We are planning to expand, we are planning to build up on what we have at the moment, and Shanghai lectures are very relevant to both students and staff at this university, and robotics is very high on the priority list at our university. Thank you very much. We're looking forward to this new, exciting year. Actually, it's always hype. It's always a great hype for our students to participate in these courses. Thank you.
Thank you. Thank you. So, I just for the other groups, I remember that last year the team from Moscow was actually involved even in the koans, no? This very challenging project that we give to the students, and they performed very well. You know, so.
Thank you. It was very, very encouraging. And our students are looking forward to working in teams, international teams.
Yeah. So I think it's very nice to so I think that's why you did it, no? But I think it's a very nice to see that you value artificial intelligence in the humanities. I think I really agree. Of course, I am biased, but I think it's a very productive idea. Yeah. Thank you for your presentation.
Thank you. Pleasure.
So, I don't know if we have a news from Xian. Okay, so I continue with the basic lecture. So, actually, for the time that we have been able to follow it, we have seen a very nice presentation from Searle, actually more detailed but the few hints that more detailed with a few hints that we gave before, and this should actually encourage students to do students' presentation on detailed issues, but also to raise big questions, because there are many open big questions. So, reconnecting to what Rolf was saying last time, the situation with AI right now is that it's an extremely successful field as a discipline, because if you think to Google is one of the biggest company in the world. No? Even people fearing that Google will take over the world. No? So, and this is the kind of AI that sometimes it seems we dismiss a bit, no, because it's not embodied. So AI has been extremely successful in some things. For example, Google search in chess. You know that there are very few humans which can hope to seldom win against a computer. In manufacturing, you know that there are entire area of production which are almost completely automated. So if you think to car manufacturing, so an item which is very common, the contribution to the cost of the workforce is about 8%, and it is going down. So I mean, we have areas where really you need robots, you need artificial intelligence, you need good old-fashioned AI. Then there have been some failure. So, for instance, it's very difficult to found behavior. So, it's very difficult to cope with the problem of avoiding that your robot falls from the stairs if something goes wrong. So, you can maybe improve and improve and improve, but this kind of approach is a bit limited under that respect. When we have problem problem in natural language understanding. So we, at the moment, there is also progress, mainly based on statistics methods, based on extension to Bayes rule. But for example, now we have a kind of 65% ceiling that current methods are not able in natural language understanding, but current methods seems unable. And then the interaction with real world is really difficult for robots. So simply understanding what's in the room, so understanding that this is a net, it is not simple for a machine. For a machine like those that we have developed so far. And so just coming back to a slide that we have seen already last time, so we use very different methods, for instance, in the factories, with respect to the methods which nature have evolved in animals and humans. So on one side we have high accuracy, which we obtain by heavy weights, basically, and very detailed programming. On the other hand, we have low precision, compliance, so we don't have rigid, many rigid parts in our body, reactive, and we have a capability to cope with uncertainty, which is essential. One of the things which are really unmatched by our artifacts so far. No? And so, how we can put the labels, no? Because we do it very naturally. Actually, we do it very naturally after several years of training, but we can do it. No? And so we have this paradigm shift that we strongly advocate, which is to pass from an idea of cognition as computation, so state machines evolving from a state to the other one. And I would say that in the Chinese room experiment, as it is proposed by Searle, it seems to think that this big book is a kind of big lookup table. So, and this might be a weakness of the argument. In favor, we push, we advocate a more sophisticated idea of cognition as an emergent behavior coming from the sensory, motor, and interaction processes. This is more difficult to say, it's maybe easier to say than to do, but we will see in next lectures, in particular, but actually many lectures, but in particular on the lecture on developmental robotics, that we already have some early success in this direction. Talking on that, so you also can read this is a kind of best practice book, no? So while we are clearly very far from mimicking the kind of processes that we have seen in the cell, then we can learn some lesson from this consideration and to do something. We will come back in the last lecture when Barbara Mazzolai from the IIT in Pisa, we will talk about the very cool work they are doing on plant robotics and plant intelligence, so vegetal intelligence, which on the surface seems to be contradicting what David Wolfert said, that essentially animals have brains because they need to move, right? So they are less, it may be less contradictory, but we will discuss this. So what talking about what we can do without no, we have seen the frame of reference problem. No, from where comes the problem? That an ant of a dimension of an ant on the beach will, so to speak, work, because the behavior is coming from interaction of the agent and the environment, and what the agent is doing in the environment. But if you do this Foyt experiment, no, and you multiply that 100 times or 1,000 times or even more the dimension of the ants will stop behaving as you are used to see ants behave. So the point is that we have to consider the characteristic of complete agents. For instance, look into an old comics from Japan. This could be an example of a complete agent. It is a fictitious one, but it has the capability to interact with the environment. So this is a strong point that we raise, but what we actually say is that we don't believe that an artificial intelligence can really exist if not connected to a physical system. At least we would like to see the AI on a moving robot. And so what happens to the then? So then the complication, the complexity rises to the fact that the system that now we study is a system which is, I cannot only consider algorithmic rules. I also need to consider the laws of physics, dynamical system characteristics, and the fact that, for instance, if I want to understand if this spot of color that I have here, think about, so you are in charge of recognizing the object on my desk. Now you don't see it, but if you can interact with the system through me, in this case, as a teleoperator arm, now you understand that it is a pen. So actually, this doesn't require to implement a completely new intelligent system, but the simple consideration that moving the object may help the recognition is also of help if you use standard computer vision techniques, or even standard vision, right? So if I move it, you understand what it is. It could not be a pen, because you trust me, but you should check if it can write something. So since we are short of time, I leave this as a suggestion for a future student presentation. So we have seen that when talking about the biological system, we have seen that we have multiple parallel stochastic processes, we have emerging self-organizing behaviors, we have a lot of non-linearity. So what do we mean with non-linearity? Of course, we mean a system where the superposition of effects doesn't hold. So in a linear system, if you do a small change in the input, you have a small change in the output. If you sum to small input, you have a bigger output. In a nonlinear system, you have a typical butterfly effect. So you can have a small change in the input, which leads to a huge change in the output, and the opposite. So this is actually that is not usually exploited, but happens continuously. And due to the sinus and cosinus, every arm is actually non-linear by definition. The fact that we control it as a linear system forces us to do many assumptions and to limit a lot the possible behaviors. So the workspace, for instance, we need heavy. So one main reason for the fact that welding robots in the factory are heavy is that to stay in the linear, we need to reduce the non-linearity of emotion, and to do that, to do a heavy robot is the easy way, no? And it's not so easy because it takes a lot of engineering work to build a good, stupid welding robot. So we have to consider many things. So the trajectory in the phase space, the dynamic. So it's a completely, it's a field that usually is not part of a standard curriculum of a person working in AI. But what And that's why probably we are still not there completely. So we need really a multidisciplinary or a transdisciplinary approach. So people knowing at least, or at least being able to interact with people with a different knowledge base. No? So I now come to design principles that are essentially, this design principle have to be seen as guidelines for design. And I think also as a challenge for design, because as we will see when we will go forward in the lectures, there are still open issues. So the good and the bad of this paradigm of embodied intelligence is that it is very convincing. When we want to build a system based on this principle, we miss many modeling tools. No? For instance, a comment that Ozda, no, from Professor Ozda from Osaka received in the first lecture was, yes, but how you control your bionic robot? Yes, how we control the bionic robot. This is a research challenge. So the nice point if you have a researcher is that there are many deep problems to solve, and this is good if you have research. But if you want to really use them in the real world and to exploit the benefits in economical terms, also economical terms, which makes sense, we need to do some work. You know? So, and this is very, so let's enumerate, let's discuss the principle that we should follow into the design. So the first of this, we will see them maybe not all today, but in the next lecture too. So the first one of these principles is the Three-constituents principle, as Rolf calls in our course handbook. So at least when designing an agent, and if you think to the ant moving on the beach, this should be clear, we need to consider the ecological niche, meaning the environment where this agent is going to act. So it's not the same if you have an ant the dimensions of an ant, or if you have an ant the dimension of a skyscraper. So you cannot design the control in the same way. The second is to consider the task. So your system may not, so because sometimes in AI we have this idea that we want to build immediately, seems sometimes that we want to build immediately, to mimic immediately the high level of a human brain. No? We want to build a companion, but in the sense, not in the sense of a robot companion, but a companion in the sense that people, entertaining people with whom I can have nice discussions. No, there are lower level of for instance, ants are not very good in discussion of Russian literature, right? But they can do many things. So the behaviors and tasks that you want to implement are important. And then how the agent is really built. So if I have a legged robot similar to an ant, I will need to implement a different control than the control that I can implement, and a different morphology. Because when I say that I want to consider the agent, I also mean the morphology, because how the agent is shaped as a consequence on what it can do. For instance, coming back to what I was saying before, no? That even if in a mixed, let's say, mixed paradigm approach, no? Like those referred to by this experiment by Mehta and Fitzpatrick several years ago. So you can have, let's call it standard computer vision. You can have a standard control of a rigid body, multi-body but rigid multi-body robot, and still have benefits. So in this paper by Mehta and Fitzpatrick, you see that actually moving things, like we also do, no? So moving things, so interacting physically with the object that I'm recognizing can help to understand what I'm recognizing. No? So this can be done even in a completely standard with a standard approach. Then we have ambition, maybe not.
Welcome to Life Size. Enter the extension of the person you want to call or the meeting you want to join and press pound.
Yeah, I think probably. I try to continue. No, so and again, so in the perspective of building a system based on the principle of operation of a cell, what I can start to do? Well, I can mimic the parallel loosely coupled processes of the biochemical information processing of a cell by a set of parallel independent processes in a computer. Again, while we move in the direction of a radically new way to build robots and artificial intelligence, we have many recipes that we can import into, let's say, a state-of-the-art, but not yet new paradigm platform. And so if I want an intelligent behavior, which is emergent, is based on many parallel, what I can do, already many years ago, in a famous paper, Rodney Brooks' paper called, which at that time was, I think, one of the seminal paper in embodied intelligent cognition, was Intelligence Without Representation. And it was in 1980 something by Rodney Brooks. The idea was quite simple. He implemented a number of behaviors, so processing, managing specific things on the same robot, working concurrently. And of course, we have some problem to fine-tune which behavior prevail over another in some condition. But you can do what he did, for instance, in a robot like this. So to have the so-called subsumption architecture. It's still, of course, you have still a computer, but the way you implement the behavior control is conceptually different than a top-down control system. So again, this is another example of the fact that while you are ready, you prepare the new materials and the new maths and control approaches for a radically new soft robotics, you can really draw many good ideas from this paradigm. Let's come back to the ant and look a bit more in detail on how the ant works. No? There is again some very good work by Holk Kruse, a German biologist, who analyzed how an ant, a small insect, works. And the nice thing that he discovered is that there is not a central control for leg coordination. So to speak, every leg has its own independent control, sensing and actuation. and how the legs are synchronized between them, essentially by means of what is called stigmergy. Stigmergy means that they actually, depending on the movement of another hand, the position of the body will be different, and so the other hand will sense something different. So this kind of loose coordination, so every, let's say, independent wheels, independent legs, are coordinated essentially by the fact that they are in the environment. So if you thought that the frame of reference example of the ants on the beach was a good example, this is even more. So the ant can walk because there is the sand, otherwise it couldn't. No? And this leads to have, is made by angle sensors, to be a bit more detailed, but the idea is that each leg has its own sensor and actuator. And the neural circuits we see are simpler, but are still very complicated with respect to a standard computer. So, so to speak, we need more computing power, and this is more or less confident that we will have in the future. But this points to the fact that we also need so we need to consider the embodiment. Sorry if I repeat this. And then let's look at an application to social interaction based on the subsumption architecture. So this is, maybe we can show the video now by Kismet video.
You're a pretty funny person.
You see, you get the appearance of an appropriate basic social behavior by implementing some reflexes. So, of course, here you have another nice question that you may mumble about, which is so what we consider social cues are just reflexes. Maybe not completely, but many things are really simple behavior, no? Because if you look here, you have the appearance of an appropriate behavior. No? It's even cute, right? And now we can see a recent application based on this principle. Nathan, can you show the other video, the Jibo video?
This is your house. This is your car. This is your toothbrush.
Just in case, I think this is just blue sky research for, let's say, that you decidedly pursue for cultural and aesthetic or humanistic reasons. This is it's not yet a product. It's an idea of a product, but this is something that a company actually led by Cinzia Briesel is currently developed. No? So you see, this is not a dramatic. So this is more than you can do now, but not that more. So this is not dramatically conscious intelligence. It's not huge intelligence, but you see that it's more than enough to allow some interaction function and some useful function in your daily life. No, so we have to be careful, because while we chase the goal and the long-term objective, many fallout technologies may actually solve everyday problems, no? And this usually translates into having an economical impact, no? So maybe overreaching, but usually not always, but usually you get money from the community, even in a free market. So in a free market, but I think in many systems, you get some reward from the community when you solve some real problem of the community. This is an example of how, without implementing really artificial intelligence in the strong term, you can develop things which are useful. So, and just since we are already entering into the break, I want to pass to maybe to another example, and then we can finish. Yeah. So the example of puppy slow motion. Let's pass to puppy slow motion directly. Okay. So, and that was, so the systems that we saw before actually use motion as social cues, no? So they move to be able to interact. If we look and they have some intelligence in the sense of they have some control program inside. Now, let's go on the other side, and let's see how we can obtain nice motion behaviors like those that we see in this short video. So, what's really noticeable about this system? This system is that it is a bionic system on a treadmill, but you may guess, so we are out of time, but quickly think which kind of control is inside the puppy robot, which was, by the way, by Fumiya Ida, which is a former student of Rolf and is now in Cambridge and ATH, as far as I know. Think about it for a while. So the nice point is that there is no control. Or almost no control. So this points to the concept which is central to the problem of embodied intelligence, which is morphological computation, meaning a huge part of the actual behavior in the world of a system is not actually coming from some kind of computation, but is coming from emerges from the interaction between the agent and the environment, given the task, in this case, working on the treadmill. This is an important insight, and we will elaborate more in the next lecture on this point. We just can finish it by saying that it's also basic to understand why a new strongly emerging field like soft robotics may have some value in the future. So so it's good, it's reasonable that we have this interest for soft robotics, because the fact that we have a soft end actually simplify a lot the problem of grasping an object that I don't know how it is made. I don't know the shape of this object. So with this consideration, I want to close here. I'm afraid that we don't have much time for a question, but maybe if one quick question, if you have one quick question. Okay, so we can stop here and we can start again in 5 minutes from now at 10:15 with a lecture by Vincent Muller from Anatolia College and Oxford with about a topic which is related to this, for instance, the example of product that we saw before. No? So, okay, it's nice, it's useful, but to which extent we can develop artificial intelligence robots and to put them into our daily environment, including battlefield environment. But Vincent will will discuss this later. So see you in 5 minutes. Thank you. And I want to give a special thanks to people from Asia, from China and Japan, in particular, for staying here with us until very late. So thank you, everybody, and see you next week. Thank you.
Thanks.